Hello, my name is Gracie Dahl, and I recently graduated from the University of Cincinnati's Environmental Engineering undergraduate program, and I also graduated from the MBA graduate program.
My name's CJ Mead. I am also a recently graduated environmental engineering student from the University of Cincinnati. And the other students who also worked on this project are Kanan Harrison, Sinceri Gentry, and Kara Hall, also environmental engineering students. And in addition to the 5 undergraduate students involved, we were assisted by graduate students Yu Zhang and Junqi Lia under the direction of professors Mingming Liu and Maobing Tu. Our project is practical PFAS treatment with sawdust, and we completed it at the University of Cincinnati.
The goal of this project is to develop a practical, efficient, and cost-effective approach to treat PFAS, especially PFOA and PFOS, in drinking water using functionalized sawdust biomass. This project impacts people, prosperity, and planet in the following ways. For people, PFAS has potential health effects and toxicity. This project works to develop a solution to reduce PFOS and PFOA in drinking water in Cincinnati and meet the EPA guidelines, thus reducing this risk. For prosperity, this project shows significant economic benefits, such as new jobs in forestry and environmental industry, a highly cost-effective way to remove PFAS, and it has the potential to develop waste-free processes. For the planet, this project reduces the environmental risks and has the potential to protect the environment and improve the water quality in local communities, such as Cincinnati.
To functionalize sawdust, the research team completed several iterations of the chemical process by which the sawdust was ionized. Raw sawdust was reacted with epichlorohydrin and dimethylamine in an alkaline solution to create a biomass-based anion exchange resin, which can be seen in the photographs here. To test the PFAS removal efficiency, we have compared our functionalized sawdust with commercial activated carbon and raw sawdust. Through the experiment, we found our functionalized sawdust removed more than 92.41% of PFOA and 83.85% of PFOS.
To determine the absorption kinetics, we have fitted the experimental data to the pseudo-second order reaction and found out a relative high absorption rate, constant, and initial absorption rate for both PFOA and PFOS. To evaluate the absorption capacity for functionalized sawdust, Langmuir and Freundlich models were adopted to describe the experimental data. A good fit with the Langmuir model indicated a monolayer absorption of PFAS on the functionalized sawdust. We also find that our functionalized sawdust possesses high absorption capacity at 209.26 milligrams per gram for PFOA and 161.80 milligrams per gram for PFOS.
To expand our study with more PFAS compounds, we've worked together with our analytical center in our department to develop a practical analytical method with LC-QTOF to identify and quantify 13 PFAS compounds. Each peak in this figure represents one compound. This would help us to test more PFAS compounds in our future work.
As this project progresses, there are 4 more steps that need to be completed. The first is column testing. A PFAS stock solution will be run through the absorption column that has already been prepared. One round will pass through the activated carbon and the other through our functionalized sawdust to determine how PFAS removal compares between the two mediums. The spent functionalized sawdust will then need to be incinerated to determine if the burning of the functionalized sawdust waste will result in unintended pollution to the air. The third step would be replication of the column testing process with different PFAS compounds to ensure the process is effective across the board. And finally, an economic analysis will determine the economic feasibility of functionalized sawdust as a PFAS removal technique. The following conclusions have been reached through this project. Commercial sawdust has been functionalized into biomass-based anion exchange resins, which is highly efficient and cost-effective for PFAS removal. Absorption isotherms suggested that the synthesized functionalized sawdust showed high removal efficiency and high absorption capacity for PFOA and PFAS removal. Absorption kinetics indicated the absorption of PFOA and PFOS on functionalized sawdust was very fast, within 2 hours. Functionalized sawdust will be an excellent material to remove PFOA and PFOS in the tested water. The functionalized sawdust could help EPA to develop innovative methods to treat and manage PFOA and PFOS in water systems.